So the first thing is, why do we need standard errors? Uh, because of the fact that we are using one sample of size n, and we have sampled n observations from a population of size n. Of course, capital N is greater than small n, so there will be a lot of difference. Not only capital N is greater than small n, but there will be a huge difference between these two numbers. Now, this is one sample, and on the basis of this sample, if you go on calculating beta 1 hat, which is an estimator of true beta 1, and beta 2 hat, which is an estimator of true beta 2, these are the two parameters which we are interested in, and that's what we need to know more about. These are the two things here in simple regression, and what we have are the estimators. Now, if you change the sample, if you take another sample of the same size and you call it sample 2 from the same population of size n, capital N, then you would get some other values for beta 1 hat and beta 2 hat. These two again will be the estimators of the same two parameters, beta 1 and beta 2, which are constant. If you repeat this process many times, the question that how many times, you have to collect all possible samples of size small n from the same population of size capital N. All possible samples are a lot of samples. Each time you will get a beta 1 and a beta 2 hat, which will be different from the last sample. Now you can record these beta 1 hat, beta 2 hat. You got a lot of values. This gives us a distribution of sample statistics. Let us take beta 2 hat. The distribution or probability distribution of beta 2 hat is given here in this column. Now, we need to connect between the sample statistics, beta 1 hat and beta 2 hat, and the population parameters, beta 1 and beta 2. To connect these two, we need to have some measure of precision. Some measure of precision. How precise is a given value of beta 2 hat? By precision, what I mean to say is that how close it is to the true beta 2, right? Although we don't know the true beta 2, we have methods that will make us understand how precise our beta 2 hat is. And standard error is an important contributor to this whole mechanism of using an estimator beta 2 hat to say something about the population parameter beta 2. In fact, standard error is a measure of precision. Standard error beta 2 hat is a measure of precision of our calculated beta 2 hat. So if you know that your beta 2 hat is 2.3 for sample that you have collected, let me call it the first sample. In reality, we are not going to collect a second sample. So whatever we have to do with this sample 1. So we have sample 1 of size n, which is one of the many possible samples. And that's the only sample we have. And we used it to calculate beta 2 hat, and it turns out to be 2.3. Now, how precise is this 2.3 is a question we are asking. How precise it is, for this, we need to know what is the standard error of beta 2 hat. Because
Excuse me, sir. A few students are waiting, so can you please let them in?
so we need to know what is the standard error of beta 2 hat to to answer the question that how precise is this 2.3. Last time we calculated standard error using formulas. Uh, these are the two formulas that we use.
Sir, so can we say that residual is the measure of forecast or an uh, e- or it helps in forecasting, whereas standard error helps in calculating the accuracy?
Standard error is a measure of precision. So you are right in the second step.
Yes. And the first one, like residual, is the difference between our estimated values and the values we observed. So
Hmm.
it helps in a better forecast. Can we say that?
Yes, you can say it helps in forecasting. You can say that.
All right, so thank you so much.
Yeah. So last time we calculated standard errors using these
Uh,
formulas.
so sorry. Another thing, to calculate the standard error, we always need the population, right? Like
Yes,
for example, if I have never conducted a census, I can never calculate the standard error.
yes. But there is a connect between uh, a population parameter known as sigma and a sample statistic known as sigma hat. You can calculate sigma hat, and then because it is an estimator of sigma, you can take it for granted that this value of sigma hat is equal to the population parameter sigma. So here in this calculation also this fact is evident because we need to have two things. One is we need to have sigma, which is a population parameter, which we do not have access to. And another thing is we need the x values and the deviations from x and the squared deviations from x and all the related things. So the bottom line is we need x values. So these are two things we need, x values and sigma. X values are the sample x values, so we have them. And uh, sigma is population parameter, which we don't have, but we make this assumption that sigma hat is equal to sigma. And we replace sigma by sigma hat in this formula for standard error. Because now why we do it? Because we do not have any other way, right? This is the best possible thing that we can do. There is no other way to make a connect. So we have to assume it, and there is no other way, so we do it. Now, the concept of standard error, as we discussed last time, it is nothing but standard deviation of the sampling distribution. So we discussed what is a sampling distribution of the estimator. So we took beta 2 hat. So if you take the standard deviation of that sampling distribution of the estimator, that is nothing but standard error. So that's the definition. How do we understand standard error? What does it signify? What it stands for? Standard error stands for a number which is nothing but standard deviation of what? Of sampling distribution of the estimator. So there are some estimators, and beta 2 hat is one of the estimators. So if we are talking about standard error of beta 2 hat, then we need to have a sampling distribution of beta 2 hat, and then we can easily calculate the standard deviation of this sampling distribution of beta 2 hat, which is nothing but standard error beta 2 hat. Why we call it standard error and not standard deviation is just to differentiate between any variable x of which you can calculate standard deviation and an estimator beta 2 hat of which you can calculate standard deviation, but you would call it standard error, right? So to differentiate between any variable x and its standard error, which is going to be nothing but standard deviation, we don't call it standard error, and an estimator or and its standard deviation should be called a standard error, right? So what is a sampling distribution? It's simply a probability of frequency distribution of the estimator. So how do we get those values? We got the values from all possible samples of the same size from a given population. So a very clear definition is given here. Now, if you are connecting the concept with the formula, you might not be able to connect it. You will be able to connect it better with what the definition is saying and what the formula is saying by proving mathematically these two formulas, right? So which we shall see. We will see the proof also, right? Right now, we are trying to understand the concept, the definition, and we are trying to understand the calculation. And calculation requires a formula, and we have this formula. You have to take it for granted, as we have not proved it, that this is indeed the formula. So last time we used it and we calculated this quantity, and I said that you can calculate this quantity and then verify your answer from the output of MS Excel, right? So I'm sure you would have done it, and you would have got the same answer as given in the Excel output for standard error beta 1 hat, because these are the quantities which are known. Sigma was also calculated while calculating standard error beta 2 hat, so you don't need to calculate this part also, just the manipulation of x values, and then you will get the standard error beta 1 hat. So that's what we did. Now, we understood the concept of standard error, we understood the formula, we understood the calculation. Now, let us understand the concept of sigma. This part which is there in the numerator of these two formulas. Now, sigma is called as standard error of regression, right? So this is the popular name for it. Sigma is the standard error of regression, right? And sigma squared is the variance of regression. So I'll call these two quantities by these names: standard error of regression and variance of regression. So please keep it in mind what I'm referring to when I say standard error of regression, I'm referring to sigma. And when I'm saying variance of regression, I'm referring to squared. All right. Now, the concept of sigma. Basically, whenever you run a regression, you have a sample, say 100 values of y and 100 values of x. And for each pair of y and x, you have a residual. And you call it ui hat. So if there are 100 values of x, and if there are 100 values of y, so you have a sample size n equals 100, then you would have 100 residuals also, or 100 ui hats, right? Now these, what do these ui hats stand for? They stand for errors. Let me revise it for you. So if you have a y value and then you fit a regression line using OLS, then for the same x value, you would have a yi hat value, which is the point on the line, right? And then the difference between the actual y and the calculated y and the estimated y is the error. We call it y hat, right? So if you have yi, the actual y value, which is also there in the sample, any given value, if you subtract the estimated value, which is the point on the line for that, for the same x, of course, these are all conditional to x, then this difference is going to be the error. What does it stand for? It stands for how much error we are making when we are predicting y for a given x. So actually, when somebody gives us a x value, we predict that this is going to be the y. And what is this? This is the yi hat. We call it predicted y also. Predicted y is nothing but yi hat, right? Predicted y for a given x is yi hat. We call it estimated y also. Estimated y, predicted y, right? All the points on the line, which are yi hats. So what does this residual stands for? It stands for that what is the difference between what you have predicted and what the actual y is. So if this xi occurs, then yi should be this much, right? And it's given in the sample. So we know that for this x, this is the y. But we are predicting for this x, this is not the y, but another value, another column y I had. This is the predicted y. So we predict our y to be yi hat instead of yi. Then we make an error in the prediction, and that error is ui hat. This is for sample, right? The more important variable is ui, which we don't have, right? In the sample, we have everything, but because we have our y, we have our x, and that's it. We have everything now. So we calculated beta 1 hat and beta 2 hat. So we have the intercept, we have the slope, we have the actual y's, we have estimated y's, we have residuals, we have everything, right? There's nothing which is missing in this in a sample, right? The more important thing is the things which we don't have, and we want to say something about them. Anyways, let's not go into that discussion. Uh, I am trying to make you understand that what does a residual mean. So that's what a residual means. Now, all the residuals, if you square them, and if you add them, you would get a quantity called summation ui hat squared, sum of squared residuals, right? This is the thing that we minimized in the method of OLS. Minimize sum of residuals squared, or squared sum of residuals, right? The same quantity If you take it per unit, summation ui hat squared per unit, right? Per unit means if there are many sample values, this is a number, right? It can be 2. So this is 2 for the entire sample. So how much it is per unit sample? So if there are 100, sample size is
Sir,
100, then
so this is for a sample or for a population?
this
Or
is for
like all the
you can see the hat
residual
here.
error?
If there is a hat, it's going to be the sample, right? So
Sir, but for a sample, for even for a residual error of a sample, we need a sample distribution. So if there is a sample distribution, it may not, like I may not take all the samples, right? I may only take one sample out of the entire population, or I may take only two sample out of the population.
we are taking only one sample and we are talking about one sample only.
So, sir, so the distribution will be made like, for example, x is 10, and there are, and there is one value corresponding to it. Say, suppose 2. So, 10 to 23, 44. So, this is you're calling the distribution. Is
I'm not
that
calling,
so?
I'm not saying anything about distribution in this discussion. I have not used this word distribution here, right? When I was discussing the standard error, there I said the distribution that we collect all the samples, and then if we collect it, and then if we take all the estimators, then that will be the distribution, sampling distribution of the
So,
estimators.
sample error was for population. This error is for sample.
Yeah, so whenever you see a residual, we are talking about a sample only. That's why I'm drawing the table also, so that there is no confusion that this is a sample of 100, of size 100, suppose. And for this sample, there are 100 values of y, 100 values of x, so there will be 100 values of residual. So
All
I'm talking
right,
about
sir. So
one.
we can we can say that sample error helped us tell how precise our regression equation was for a given was for a given situation that we were analyzing, whereas this residual error tells us how better or how well we can forecast our a sample regression function.
Look, the things which I am not saying, uh, you are saying these things. I'm not saying these things, that how well we will forecast, right? I'm not saying that this is going to help us in forecasting straight away. And I'm not saying anything about forecasting. You are adding this word to my discussion, right? I'm saying simple things. I'm saying that there are 100 sample values, sample size is 100. For each of these pairs of observations, we have a residual. So we have 100 residuals. So what is a residual? I just explained here. What is a residual? Of course, we are talking about one sample, as I did never said that in this discussion that we are going to collect another sample. There is one sample of size 100. So there are 100 y's and 100 x's, and there are 100 residuals. And each of these residual is defined like this, right? So what is the meaning of a residual is this. We are saying that for a given x, y is this much, y I had, but actually it is not, because actual y is yi. And the difference between what we have predicted, y I had, and what y is, yi, is the residual. Then I explained, if you take all the residuals, and then if you square them and add them, you get sum of squared residuals. And this is one number for the whole regression. This is not a variable. Summation u I hat squared is not a variable or a sample. It's a constant. It is one number, right? So it represents the entire regression. sum of squared residuals represent one regression. It's a one number. It can be two, it can be five, right? This number represents the entire regression. So it represents entire 100 observations. Let us take per unit of it. So we have to divide it by n. So if we divide it by n, but there's one little difference. We are not dividing it by n. We are dividing by 2 less than n. So instead of 100, we are dividing it by 98, right? But conceptually, this is per unit, right? I will explain why n minus 2, why not n. I will explain it later, right? Right now, conceptually you have to understand that this number, this quantity is for entire regression, and if we take per unit of it, so we have to divide it by n, but we are dividing it by n minus 2. Take it for granted right now. So if we take per unit of it, what we get is sigma hat squared, which is the variance of regression that I explained here. You can put a hat here and it will become a sample statistic, right? So that's the variance of regression. And if you take the square root of it, that's the standard error of regression. This is the quantity that we are using in these two formulas here, sigma and sigma, right? So my goal was to make you understand the formula. That's why I stretched this explanation, that when I explained you what is standard error, how it is calculated, then I explained you what are the parts of it. One important part, two important parts were there. One was sigma, another was x's. X's we already have, these are simple calculations. Conceptually, you might be confused in what is sigma. So that's why I explained how do we get this sigma and what actually is this sigma and what does it measure, right? So now why n minus 2? I'll explain you the concept of residual sum of squares, RSS, the degrees of freedom, DF. That at that point I'll explain you why n minus 2, why not n, right? Okay, it is explained a little bit here, so I will leave it right now again. Again, I'm leaving it. I don't want to go into it right now. I'll explain it definitely. All right, so once you have understood these things, what is standard error? What does it measure? It's a measure of precision. How it is calculated, you have seen here. Of course, proof remains, so we will prove it. Then what does this sigma mean here? It is appearing in standard error formula. So I explain what is sigma, how we calculate that sigma, what it means conceptually. Then now let us understand uh, these formulas a little better, because we are trying to understand the formula. So this is just another slide which explains a little more about the formula. Uh,
Sir,
yeah.
so what does residual error or mu I hat, the thing which you just explained,
Hmm.
that help us measure? Like sigma is a measure of standard error. So
Yeah.
what is that a measure of? Like what it helps in?
Sigma. Sigma helps to measure standard error,
No, no,
right?
no. That I got, but I'm asking about this other thing which you just explained about residuals.
This thing, summation ui hat squared. This
Yeah.
thing. Okay. All right. So if do you remember we when we were using OLS, we minimized it.
Yes, sir, we did minimize it. That was the basis
And
of a formula.
yeah, so I explained you using a graph that there are y values and there are x values, and we have a point which represents a pair of y and x, right? All these
Yes, sir.
points. So if we take after fitting a line using OLS, if we take the vertical distances, these are all UIs. I explained that why, if we uh, add all of these, they are going to be zero. So why not square them and then add them? So for this whole set of numbers, for all this sample that we have plotted in this graph, there should be a number that represents how far is the line from the points, right? So this is exactly what this thing measures. So how good is our line? I made it really simple now. How good
Sir,
is our line?
so can you show it again? Like where are you putting it? I'm not able to see it. I guess there is a lag. Oh.
Okay. So I explained this in a great detail in the class when we were face to
Um,
face. If you
yeah.
remember, I used the
Yes,
board when
sir.
I
I remember the discussion and everything. I just want to see the graph. Which can you highlight that graph to something? Because there are too many graphs. Like there are two graphs and there is a lag, so it's difficult to look at which graph you're talking about. You're talking about the upper graph or the lower graph? Oh, all right, sir. Okay.
these vertical distances, these are vertical,
Yes,
right?
sir.
All these are UI hats. If you want to have a measure of how good is the line, you can add these residuals and see how much it is coming, but it will come out to be zero, right?
Yes, sir.
And,
It will.
and if you square these and then add them, they will not, the sum would not be zero.
Yeah, because they will be unidirectional then. Like they all will be plus only. No, nothing would be
Yes.
minus.
So you can think here yourself that whatever this turns out to be, suppose this turns out to be 3, right? Then what does this measure? It measures how far are the points from the line, or how far is the line from the points. So
Yes.
it's just, so this quantity, remember this quantity is one number like 3, and this quantity stands for entire regression, entire sample, right? This is one number for a sample. It represents a sample. So is it a big number? If it's a big number like 10, we say that points are far from line. If it's a small number like 2, we say points are relatively closer to the line, or line is closer to the points, right? So we got a measure in this number, summation UI hat squared, that how good is the fit, how good is the line, isn't it?
Okay, so the word which I was calling as forecast was you actually trying to say the best fitted line, which helps in
Yes.
forecast, not this. Right, sir?
I just lost you. You
Yes, sir. I was trying to say that the thing which I was calling forecast is actually best fitted line, and best
Hmm.
fitted line helps in forecasting if we want to, but that is not the but that is not its only purpose. So that is what you were trying to say.
Hmm. Look, you can say whatever you want about forecasting, right? It's your choice. I am not saying that. I am not using this word, right?
All right, sir.
Forecasting. I'm not using this word at all because, and I don't want to go into explaining forecasting and everything, right? So it has a time dimension, and then we need to think ahead of time, and there are methods that would take us to forecasting and everything. So I don't want to use this word, right?
All
So
right, sir.
if you have any understanding of it, it's okay. But uh, I'm not neither using this word and nor not saying anything about it, right?
All right, sir.
I am using the word prediction, right? I'm using the word prediction, and it is different from forecasting, right? So if you are using forecasting as synonymous with prediction, it's your choice. It is wrong, of course. You should not do like this. But prediction, if you ask me a question about prediction, what is this prediction all about? Here in this case, I explained it, right? So prediction is you are trying to predict what y is going to be for a given x, and you call it y hat. So if x is 10, what would be y hat? Maybe 5. So this is a prediction. If x is 10, what would be the y value? And it is y hat, but actually it turns out to be 7. And the difference between y and y hat, 7 minus 5 equals to 2, is the error. This is all what I'm saying, right? So if you are confusing in these two words, please don't. Forecasting is another matter, and we can econometrics deals with forecasting a lot, uh, but let's not go into forecasting part, right?
All right, sir. I guess I was using them as synonyms only. So,
Yeah, yeah.
my
No, no,
bad.
no. These are not the synonyms. As a teacher, I have to choose my words, correctly. I can't use words synonymously, which are actually not synonymous. So I take great care in choosing my words. Anyways, so uh, the last thing, this slide for today, which I want to explain is that given a value of sigma square, the larger the variation in x, the smaller the variance of beta 2 hat, and hence greater the precision with which beta 2 can be estimated. I want you to read it 2 times at least before I start my explanation. Point number one, read 2 times. Now, can anyone tell me what's going on in point number one? All right, let me explain. So if there is a given value of sigma squared, so given value of sigma squared means that suppose sigma squared is 10. The variation in x values, the larger the variation in x values, so if variation in x is large. So what is variation in x? Variance of x. And what is variance of x? It is small x squared added divided by something. So that's the numerator. So we can take it as a measure of variance of x. So let me put it like this. Greater the summation small xi squared, if this is large, for a given sigma squared, greater the summation xi squared, smaller the variance of beta 2 hat, right? So let us look here. Variance beta 2 hat, given numerator, bigger or larger the denominator, smaller the variance. So that's what is written in point number 1, right? So if variance beta 2 hat is small, precision is high, right? That is what is written in point number 1. Now, this statement, point number 1, comes from the formula. It is simply saying for a given numerator, bigger the denominator, smaller is the thing we are calculating. If the thing we are calculating is small, this thing will be high, which is precision. So given sigma squared, bigger the variance of x, smaller the beta 2 hat, and greater is the precision, right? Now think intuitively. Don't look at the formula now. Just think. We have x values which are spread a lot, right? In this case, when x is spread a lot and y is not spread that much, we have something like this, right? And then we have a line passing through them. The point is that because there's a lot of variation in x values, a lot of variation in x values, if we keep our sigma squared constant, that if we keep our this thing constant, now sigma squared comes from sum of squared residuals, right? If we keep this constant, then when we calculate variance of beta 2, so we have beta 2 and a lot of values, they will not vary much, right? So when they will not vary much, that means we will have smaller standard error or smaller variance of beta 2 hat. In that case, we will be more precise, right? Precise means our beta 2 hat will be closer to beta 2, right? So this is really interesting to say something like this using this formula, right? So this whole concept was hidden in the formula. We just uncoded it just by thinking about the formula, right? So formula is telling us that for a given sigma squared, if we are not changing the sigma squared, and if we change the variation in x, the denominator, then we will get, if we make it big, then we will get a small variance beta 2 hat. In that case, we will be more precise, right?
Excuse me, sir.
Yeah.
Sir, can you explain the more precise part once again, sir?
Okay. So what is the meaning of being more precise? More precise means that we are closer to the population parameter. Now, let me not put it like this for a moment. Let me put it in another way. So basically, if you have uh, a number on the y-axis, say 5, and there is some quantity z measured on the y-axis, right? And standard error would give us some range around this value 5, 5 plus minus 2. 5 plus 2 is 7 and 5 minus 2 is 3. So this 2 can be thought of as standard error of this 5, right? So if this 2 is not 2, suppose it is 5, that means standard error is bigger than before. Would you say that you are more precise in situation A or you are more precise in situation B? What would you say?
Situation A, sir.
Situation A is more precise. So try and understand this from this formula. Of course, we will have more understanding of it later, but try and understand from this example that when I'm saying variance is smaller or standard, when variance is smaller, standard error is also smaller, right? Because variance, square root of variance is standard error. If something is, if variance is small, standard error will also be small, right? So that's what I explained in terms of standard error. So if you don't want to understand this formula, you can take this one. Anyways, these are all the same, just square root of one is the other one. So understand precision in this way. If this thing happens to be small, 2, you will say that it is more precise. That's what we are saying here. Smaller the variance, in other words, smaller the standard error, more the precision. Did you get it?
Uh, yes, sir. Yes, sir.
Now, you can think of this formula also in this way. Point number one, right? Now, point number two, also given the variation in x values, the larger the
Yes,
values
sir.
of square.
Uh,
Yeah.
so actually, we have another class right now. So can we take this up in the next class?
Okay, sure. So we will continue this part in the next class.
All right, sir.
Yeah.
Another.
Excuse me, sir.
Yeah.
Sir.
Sir, there's one thing that, sir, your pen and the voice now, sir, lags a bit. When you write, sir, the thing comes a bit late to us. It shows a bit late to us. It lags all the time. Like
Okay.
when you're writing, we are not able to see it at the same point of time. We are able to see it like 2 or 3 seconds or 5 to 6 seconds later.
Okay.
That's
So
why
in
most
that
of the
case,
time.
what I can do is I can be a little bit slow.
Uh, okay, so maybe that will work. Because when you write now, after it shows us after when you are finished, we get to know what you have written.
Okay. So in that case, I'll try to make this lag up. I'll keep it in my mind, right? So I'll try to make it up for it, and let's see what happens. But I mean, there is no other way except using the pen and the slide. But it's good that you told me this thing, so I'll try and solve it as much as possible.
Thank you very much. So,
Okay, so Priyank, can you send me the attendance, the list of absentees?
Yes, so there are two absentees. I'll send you their names
Okay.
just after the class. And so just one another small thing.
Yeah, yeah. Sure,
So
sure.
for tomorrow's exam, so how many questions you will be asking, uh,
Uh,
and what would be their weightage?
okay, so you have exam on 19th and 20th, right?
Yes, sir. We have our exam on 19th.
And not on 20th?
No, sir.
So let us make it 20 now, not tomorrow.
Uh, a- all right, sir. Because actually on that day we already had an exam. Uh,
Okay, but now you don't have exam on 20, so let us put it on 20.
sir, we no, no, we already have our MCQ for accounts that day.
On 20.
Yes, sir. And after that, we have it for research methodology. And since money and banking date was not announced, so I believe that would also either be 20th or be uh, like 21st only, because so
Right
will
now, right now you don't have any exam on 21st.
uh, so we have our research methodology exam on 21st.
So you are busy 19, 20, 21.
Even yes, sir. And 18th we have your exam, that is tomorrow.
Okay, if you want me to have it tomorrow, we can do it.
So like you
So
will be asking us MCQ.
no, I'll be giving you theoretical questions and you have to write your exam using pen and paper